this is the Lotus Temple. It is the newly built after independence. This is one of them. I think there are 7 in the world. One is in Sydney, other is in Frankfurt, and one is in United States, and there are 3 more all over the world. They believe in one God, one unique religion and unique thought. On that basis, it was built, and this is one of the monument before British, the Mughal, they have made it. It is the tallest tower monument in Delhi. It is very, very close to our university, and this is another structure. It was a same Mughal period. This some king they have developed it. The uniqueness of this is a very good structure, a very symmetric structure. It was the inspiration for another king who built the Taj Mahal. It is just in memory of the king, of his wife, and he simply established this monument, and every people, mostly the romantic people, they used to visit these places, and we see our Mr. President Putin is here with his wife and taking photo out of it. So, as we go on my topic, it is simply we can start from the simple line that if we have a pencil and if a dream that anybody can, you can anywhere in this universe. So, it is exactly true for everybody, because we have taken pencil, we have drawn pencil, we have learned how to write, read and write, and today everybody is here. Just if you think the resource material was simply a pencil. If you talk about the graphene timeline, the timeline you say is because in graphene is not a new material, it exists almost 100 years back, but it suddenly came into light because how to take one layer, atomic layer from the graphite material, and that was really and meticulously done by 2 scientists, the Manchester scientists. That was in 2004, that is here. After that, you see there is a steep change in the rise of publications and research activity all over the world, and they were awarded Nobel Prize in 2010, and after that it is going on more and more. But by the time there is a slump here, the slump is because the other 2D materials they came into picture, that is the molybdenum sulfide, WS2 titanium sulfide. There are so many 2D layers. Now research have already started. The idea was that they may get a material very close to graphene, and the inspiration was simply by this line. If you go, that these 2 scientists who got Nobel Prize, they are here, and they simply take out one surface layer, one atomic thin. Interesting point is that they still have this honeycomb lattice structure, as you see from here, and the carbon, this twice S and 2p, these electrons they simply hybridized, and they make a sp2 bonding in the plane with 3 carbon atoms, and pz, that is this bonding, it is simply where delocalized bonding, that is where it acts like electron cloud. The carriers are simply move easily above this plane. This is the structure, and these 2 scientists they also agree that we did not do anything more, because what we have done, that the graphene is the new physics it has delivered for the science and technology for further research in the 2D materials. If you look in in the atomic lattice structure, you see this is the direct lattice, where this is the unit cell where we can generate the entire lattice, and if we transform it to the reciprocal lattice, this is the first Berlin zone, where all these properties we can simply derive, taking into the most crystalline symmetric points K, L, M, M, gamma, everything. And if you see in 2D lattice, the electronic band structure, there are 6 cups at the K points. In the K point, each K point, if you simply study, it is a cone type structure. This is different from any other semiconducting materials, because in semiconductor materials energy band structure is parabolic, whereas it is simply acting like a cone structure. Here these electrons and holes, they are behaving like a they are known Dirac fermions, and they have the massless, they do not have mass, and they move with the speed of light, very close to the speed of light, and it is called, it is not metal, though Fermi level is here, but this Fermi level does not contain any electrons. So, it is a 0 band gap semiconductors. If you see the energy band diagram of single layer and then the 2 double layers, because of the symmetry structures, you can have a energy band structure like this, but you can have some kind of mechanism, you can play some engineering of the band structure. If we apply an electric field, they will be shifted here. This shift basically we can tune it, because if you tune it, we can simply have applications, the energy band gap of the order of gigahertz, of the order of terahertz, and also people those who are interested to do some IR emission and source activities, they can also do this kind of band gap engineering in the multi-layer graphene structures. If we talk about the properties, properties is a very interesting, that is why I am told it, that it has the high, it is not readable because of the light, because it has high carrier density, surface carrier density of the order of 10 to the power 12. It has extremely electrical conductivity, much greater than this copper, and this is because of this they have the mobility which is of the order of 0.2 millions units. And one more thing, the carriers, those who are moving with high speed and they do not have mass, that is why you have the highest kind of mobility is conductivity you can imagine of. And another point is very important for the surface specific area for the sensor applications, which is also very interesting, very large. If you talk about mechanical properties, it is also a very good picture in the sense that it is harder than diamond and 300 times stronger than steel. And tensile strength, if you talk about, it is more than 1 terapascal, and strength stretchable, you can simply stretch it 20% of its initial wound size. And the last one, not the least, if in the presence of defects, graphene is the strongest material so far known, and it is as light because they do not have mass. You can simply lift that graphene layer even as a lotus leaf, lotus flower. Heat conductivity, which is very important for our temperature sensor, you can see there is the highest around 5000 watt per millikel per meter per Kelvin, and this is because you can simply use this material as a sink in the transistor, the electronic circuits devices, because heat generation is a very serious issue and that need to be vented out. So, graphene can be used to vent these heats from the devices. So, that way it is very applicable. Not only that, if you talk about optical properties, then 97% light simply get transmitted and 2.3% light simply get absorbed. So, whatever optical property you study, it is just because of this 2.3% of light which is absorbed. And because of this high transparency, this material can be used as a transparent electrode, just like a replacement of ITO. And you can see in naked eye, graphene is also easily you can see the graphene positions in between two, the bilayer, this is here and this is the pure graphene. It is visible in the naked eye also. So, a close look, it is just my some kind of imagination that if we go to Indian mythology, there are some answers and questions there. Mythology says that we have one god that is called, it's just not a joke, we have one god that is called the mother carbon, or some people say it is a force of nature force. What is so great about it? It says that everything is created out of darkness. When there was no sun, no moon, and the interplanets of the earth, nothing was there. The darkness, the whole planet is created. This is what our mythology means, it is the Hindu mythology basically. And this darkness is basically, it symbolizes as a carbon. Okay. Another important thing why I want to insist it, she appears in the mythology in 10 different forms, physical forms. Somehow it is just like a devil, somehow it is just like a very good beautiful wife of Shiva, the another god. So, this way I can simply resemble, it is also in the mythology it mentions that if carbon is the behind this creation of this god, and this god is well respected not only in India, in various parts of India, it is also respected in Bangladesh, in Sri Lanka and in Nepal very much. So, Now, we look at the carbon side. Carbon has very powerful material that we have seen it because of its properties. Another important thing is this: carbon exists so far in 5 different forms. It has 5 allotropes. It is carbon nanotechnology, it has graphene, it has fullerene, it has carbon this carbon ribbon, and apart from diamond also for this. So, people think, I mean, all the scientists now have pondered these questions. So, why not try to find out some other 5 elements to make it equal with this goddess. So, I request this next generation, that it is up to the next generation to discover 5 other elements which are still not yet. So, if I happen to meet all these people, I will request and show them these slides, that please try on to discover another 5, because it is not the end. So, now question is, how many ways we can simply produce graphene? This is a very tough job. It looks very to take out one layer. How do you take it out? The process that is shown by these 2 scientists, this Manchester scientist who got Nobel Prize in 2010, they have utilized this formula. Simply take out by Scotch tape, taking out one layer, and that is all. But to work with the graphene, it is not easy, because you have to maintain it in the inert atmosphere, and it is very difficult to protect them from other impurities. Or do one thing, that we take a graphite oxide and simply do dispersion in and ultrasonic agents in liquids, and then we can also take it out one by one layer. Other option is there, that we can simply use a very known graphic growth technique, that is called the chemical vapor deposition technique. By this way, we can also epitaxially grow this graphene layer on the silicon carbide or maybe silicon dioxide. The entire process is very much the organic synthesis. This is what these 2 scientists, the Nobel laureates, have done it, that I have told already, but there are some advantages, that it is a low cost. You do not need any very high end equipment to do that, and synthesis, you can also tune the number of layers not so easily, but you can do it. Limitation is there, the film is uneven, wrinkled on the top surface. Second thing, it is not reproducible, because one layer, 2 layer, but you are not sure that you are getting every time 1 layer, 2 layer of the similar natures. And the most important point is that it has low production yield. How can I make an industry of graphene based devices where the yield is very much, very low, very poor quality, and the process time is very time consuming. These are the 2 important points the people have thought about it, how to avoid this, how to bypass this path, and if we simply talk about some alternative paths. So, these hurdles basically did not allow graphene to be used in the pristine form. So, we have to think the other means, that how we can create a graphene like material, not exactly graphene, but at least if it is very close to the graphene properties, why not? This is some synthesis route, already the chemistry people they are doing it. Right now, there is simple route is this Hammer's method, that is the reduced graphene oxide and the reduced graphene oxide. We take, for the sake of simplicity, we take graphite and then we do oxidations, we get these structures. There are so many functionalizations on the top surface and the side surfaces, and then we simply disperse it in some solution and do ultrasonic agents and simply exfoliate one by one layer like this. Can we manage with this layer? A good question right now. Does it show exactly the graphene like properties? If it is that, we can take it easily without any hassle, but picture is not rosy, because nature does not allow you to go so simply and so quickly to achieve that. Another option is that you can reduce it by chemically or by thermally, so that we can get a graphene like structure, but there are still some functional elements are attached with it. If it is 10% or 20%, we do not mind it, but this job does not take too much time, does not take too much money, does not take so many high end equipment. So, we can come back this structure very easily. Now, if we get it, we will make some devices so that it can be useful, and it can, interesting point and the positive point is that it is reproducible. You can create bulk and commercial activity can start on. But there are some adverse issues because of the light. I can simply say go to the back slide. Adverse issues, what they are? Because these are the functional elements, they are on the top surface. They are basically create insulating layer. because graphene the conductivity of graphene is getting highly reduced because of these functional elements. Second point is that they create disruptor in the lattice sites. If the lattice site is disrupted, then this conjugated network of the conductivity that simply breaks down. So, as a whole we do not get any conductive path in this graphene oxide surface. So, that is for electrical purpose, for the transistor purpose, for making transistors, this is not friendly. Okay. Third point is that how easy to remove these functional elements. Is it so easy to remove this one on the top surface on the basal plane, or it is too easy on the surroundings in the edge factors? These two also will need to be studied. So, this is what I told it. So, overall if these functional elements are there, then this material behaves like simply an insulating surface, as I showed it here. And second thing, how the degree of the functional elements be present there, that will simply creates the density of carrier density, that is also a degree, how much defect is there. Then according to that point, that level, defect level, the carrier concentration will be there, and accordingly the electrical transport will simply depends on this. But there is a ray of hope that by doing some chemical reduction process, earlier it was oxidization process, now we are doing chemical reduction process. By this process we will try to solve these issues. But this reduction process, as I said here, there are two ways we can do it. The most simplest one this is, another simplest one by thermal heating in the inert atmosphere. The oxygen elements simply get out and the remaining the simply carbon structure will remain. Here by doing some hydrogen hydrate, we are doing some chemicals, again some mixing, and for some times we simply ultrasonicate it, and after synthesis, all synthesis process, this chemical this functional parts gets removed to a certain extent, of course not 100%, certain extent, and that is we can manage it for making our devices. So, if we do chemical reduction mechanisms, again there is some questions are there. Question is there, can you simply fully eliminate the functional elements on the top surface and the side surface? Can we restore the graphene structure, lattice structure, the honeycomb structure? If it is that, our problem is solved. Can we, if it is there, then what is the level of defects are there, because that simply disrupts the lattice structure. If the lattice structure is disrupted, then the conjugated network is disrupted, then the electrical conductivity is disrupted. If that exists 20%, I told 100% cannot be done, but if 20% exists, then we can decrease or increase the defect density and also the carrier density. To answer these questions, do it systematically, we need two things very clearly, that we need an improved understanding of this reduction mechanism. This is not simple process. Another thing, the complexity of chemical reaction is a very difficult process. And third thing, we need some means to monitor this process, how it is going on. As a whole, these days till now, the people are simply doing some kind of computer simulation on the molecular dynamics. This way they try to monitor how the reaction mechanism is going on. So, the question is, in summary we can talk about by reduction process that we have to eliminate the functional groups and we have to simply heal the carbon structure. If some carbon lattice defects are there, must 5 minutes. 5. Give me 7 minutes, I will finish it. Because then I will talk only one applications. Try my best. Okay. I think I will quick it. So, this way I have to simply do the elimination and healing. If carbon atoms gets removed it, then we have to expose it in the carbon atmosphere. So, put the carbon there to complete the hexagonal chain, then our problem is solved. So, this is what we have been doing. Now, I am coming to the simple application process. Though Professor Dimberg told about the graphene quantum dots, we are also making quantum dots, but this is not self assembled. It is a random structure, graphene quantum dot arrays. But whatever physics is required, he has told it. I am just utilizing little bit about physics, and then we simply go to the applications. This is our simple method how we make graphene, reduce graphene oxide. We make a composite, we have a beta alumina, sol, and mixing it, then we simply use this tape casting machines, and there we have a very flexible film, graphene film, it is here. After that, we simply try to characterize it, how much bonding, because the defects one, as I told, the functional groups, if they are there, they will encourage the sp3 bonding. But if it is pure carbon structure, there is no defects are there, no functional groups are there, then it is the sp2 bonding. So, I have to check it by XPS studies, the how much carbon atom bonding is there or defects bonding is there, this functional groups bonding is there. So, there is a competition between two, you can see here that carbon-carbon bond and the carbon-oxygen bonds. Carbon-oxygen bonds getting reduced with the process of reduction process as a function of time. And finally, we are getting almost 80 to 20, but this structure is very important as I see. These are the graphene structure what we have regenerated in this reduction process. Here in between the two graphene there is a cream structure, white layer. These are basically the graphene oxide, the functional groups are there. So, these layers basically acting like an insulator, as Professor said, that you have to put the quantum dots in a caged device. So, it is caged in between the surrounding the insulating layer, that is the dielectric layer. So, these are the quantum dots basically. Of course, there is no specific size. We have the size of the order of 6 nanometer to 10 nanometer. So, we have derived it from the Raman spectroscopy, of course. And next slide we can see, say it is a microscopic picture, electron microscope pictures. There is the aberration correction image, that this is the pure graphene, this is the graphene after this synthesis of graphene oxide to reduced graphene oxide. This purple color is the this graphene oxide with the functional elements, and there is some green patches are there. These are basically the holes, because the carbons have removed. So, these are the defects basically. So, if we go to the nature, we will see this one. In the color of his skin, texture of his skin, exactly it is matching with this. That is why I put it here. It is a cheetah. And microscopically, again the defects you can see from here, some from here, so all over here. So, carbon, if we do reduction process, we certainly create defects, and this is unavoidable. These defects can be repaired if we simply again expose it to the carbon atmosphere, carbon vapor, then this can be, the carbon atoms can be inserted there, and we can get a graphene like structure. This is the complementary studies that we have checked it, how we are creating sp2 bonding. This is the graphene structure, up to 5 hours is good. After that, if we do more synthesis time, then we create more damage than good. So, this is the XRT. You can see when it is a graphene oxide structure with the functional elements on the surface, that we have a peak at 12 degree Kelvin, and then if we simply do some synthesis, chemical reduction process, then with the function of power, then we see this peak is getting totally reduced. This is the reduced graphene oxide pictures. This is very much clear here. And also in the UV visible spectra, this is this graphene oxide. When the functional groups are there, when it is removed, then it is simply we are moving towards the graphene structure. This is for thermal. This is one low temperature study, we will do it. This is the temperature dependent IV characteristics, very important. This one is that we have a structure from 12 Kelvin to 100 Kelvin, even up to 200 Kelvin. We see in the lower temperature there is a threshold voltage region. In this region, as I showed quantum dot, they are behaving like a Coulomb blockade effect. It is coming here in this zone. And if we increase the temperature, we can see the blockade is simply getting removed. It is simply behaving like a normal conductor. We are not going to this. It is again this, that when we simply make a graphene to graphene oxide, then there are lots of defects because of the functional elements. These defects are to some extent, to a great extent, have been removed, but still are there, some defects are there. These defect states do contribute positively. It is not always doing something negative. This is the resistance versus temperature plot that we can see. It is at low temperature, the resistance goes of the order of gigaohm. Basically, at that time there is no current flowing in the devices, but current will flow in the devices when we simply charge the electron with some energy, and they will overcome the Coulomb barrier, the dielectric barrier, and they will simply go to the next terminals. So, that we have seen in this plot. If we simply plot it from 300 to 200 Kelvin, here it is simply the Arrhenius type of conductivity. It is this activation energy dependent, whether activation energy you have to give it to the equivalent to band gap or from the impurity state to the conduction band, that depends on basically. So, from 200 to if you go to 100, it is simply the hopping conductivity start, that is the Mott variable range, and if you go more lower and lower temperature, then the modified variable range hopping, that is known as Shklovsky variable range hopping, Shklovsky. It is some demonstration giving there. So, it is ionious type normal conductor. So, it is the looks like this. If it is a Mott devices, then the transitions from defect state to another defect states, this is filled up, this is unoccupied, and in Mott interesting point is that it will simply jump to the nearest point, of course, and secondly there is no Coulomb attraction between the two charges. But when you go another very low temperature, then the picture remains same. The only one thing is that these two states, they have a Coulombic interactions. Because of this, we have some advantage, and the temperature dependence relations get changed. It becomes T to the power minus half, and here it is T to the power minus 1/3. This is the device fabrications. We have taken a normal film there and two have contacts, and this is the heat source and sink, and this is one bias is applied just to collect the carriers if it is generated inside the film. Interesting point is that if we go to very low temperature, it is around 77 K, it is 93 K, and this is the temperature is increasing. Here you see it is behaving like a normal conductor, the function of time. The resistance is below 10 ohm. But if we decrease the temperature to a very great extent, sir, 3 slides, 3 or more, 5 slides, although I have started late, so only 5 slides.
No, I included.
Okay, no problem.
The
so,
next speaker will not have time. Okay.
And the moment we are decreasing and decreasing, one thing is here. One important point is there. This is the Coulomb oscillations, because when the current is passing, then you get a peak, and when the current simply goes away, then there is a slump, because it is behaving like a blockade situation, and again current is passing, when the electron is passing through the device, then this is. Interesting point is here, it is the 93 Kelvin that we see some envelope oscillations. Interesting point is here, this envelope oscillations, basically the amplitude of oscillations keeps on increasing if you go more and more to the lower side temperatures. Here we have played with bias, because people have done with transistors with 3-terminal devices, but here we have done with 2-terminal devices. We have seen that when you increase the temperature, the Coulomb blockade disappears, but in the lower sides, these oscillations, if you go towards more and more lower temperature, the amplitude of oscillations of the is very, very large. Same thing happens with the at defined bar, this is just 0.5 K, we have done with as a function of gate bias, the bias across the 2 terminals, and we see this is the Coulomb region where it plays a very important role. High temperature means Coulomb blockade disappears, but if we do the low temperature as well as the low this one, we have our region is this one, we can play devices as we like it. Same thing we have done with temperature at fixed temperature, but different biases, we see exactly the same phenomena. This is the Coulomb blockade phenomena as I told it, because the electrons will simply come here, because this is the insulating part, they cannot jump it. So, Coulomb barrier part has to be overcome by quantum mechanics, of course, this is there, and ultimately the electrons will come out. When the electron is simply getting full sufficient amount of energy, charging energy, it is able to cross it, and then you simply get a conductivity here, and this is the blockade part, this is the conduction part. So, this is the same picture. I have that. Okay, next. Here, when you make a thermometer of a temperature sensor, then we have to simply start your initial temperature is room temperature. Our device is kept simply dipped inside a container. Let us say it is a liquid nitrogen container at 77 K. I want to see what will happen. This is the picture at 77 K. A sudden jump from the base level to this highest level, and second thing, some oscillation is going on there, because it is Coulomb oscillations. And the for temperature sensor, the parameter is very important, that is the TCR, thermal temperature coefficient of resistance, that is coming record high, that is around 2000 values. It's so fast it will respond it, and because the TCR controls the sensing response time, also the recovery time, and the most important is the sensitivity and the resolutions. All are linked with this 2000 TCR values. So, you can see here in the next slide, the response time is 0.3 second and recovery time is almost 0.8 seconds. As this professor told that this Coulomb envelope formation, as I seen in this kind of picture, when you go see that Coulomb peaks, simply they oscillate like an envelope shape. This shape basically it depends upon. We want to explain it in terms of the coupling. There is one quantum dot here, the other dots are surrounded these devices. So, they will influence, because of this influence, this kind of this as like group velocity, phase velocity in physics, or you can say this modulation phenomena in electronics communications. Similarly, we see the effect of other quantum dots, and because of these interactions coupling, we see this phenomena is there. But when our device is basically the fixed size already made by synthesis, so we cannot change the separation between two quantum dots and the confinement of the carriers there. So, this here people can engineer their devices by playing D and L. So, they can create this phenomena. It can appear in the beginning very high temperature also, and even in the low temperature also. So, this is the resolution part. We have checked it that even if we go simply take 100 milliohm as a signal, then to measure this signal of the order of, let us say this is at 77 K, to measure we have changed a temperature 0.1 Kelvin temperature, we change this response up to 1 mega ohm. If we simply calculate the resolution of the system, we have found that we can go to even micro Kelvin. The resolution minimum change we can sense it. That is because of the high T's here. So, this is all about. I think time is over. I had another applications, but I can discuss with the people if they want later on. Thank you very much.
Ну, это переключать слайды, да?
Да, да, да.
Так, а указка лазерная здесь есть? Или
Она, по-моему, вот, по-моему, сверху кнопочка.
А, да, да. Хорошо. Hello, everybody, dear colleagues. It is really nice to see you here. It's my pleasure to see you on the International Conference of IT Technologies and Nanotechnologies here in Samara, the home of smart and beautiful people. So, my name is Sergey Arkhipov. I have just finished my PhD thesis in fiber optics. I was inscribing FBGs in anisotropic fiber optics, optical fibers. So right now I am the technical guy in special system photonics. We are specializing in distributing and implementation of different devices and solutions in the field of photonics. So you understand that I am really into the fiber optics and I love it. And I hope that you will enjoy my presentation. So the name of my presentation is Fiber Optics and Integrated Photonics and Technological Equipment. So at first we will start with Fitel Furukawa fiber fusion splicers. Then we will go with specialty fiber splicing and processing with ring of fire technology, the 3SAE. Then I will spend some time describing the FBG mass fabrication solution from Northlab. Then we will go up to auto-alignment system optical packaging solutions from FiberPro, South Korea. And we will finish our presentation with lunar high-precision reflectometers and optical vector analyzers. Okay, let's start with Fitel. So Fitel is Japanese company. It is the subsidiary company of Furukawa that was founded in 1884. It is one of the world leading manufacturers of optical fibers, fiber optic cable, fusion splicers and instruments, laser diodes and components. You have probably heard of OFS company that is fabricating just telecom and specialty fibers as well. So the company has offices in more than 40 countries. Its staff is more than 80,000 persons, and it has 8 global research and development centers. So the company's aspiration to innovations is noted by Thomson Reuters, top 100 global innovators. So Special System Photonics is the official partner of the Fitel company. Now here we see the specialty fiber fusion splicer evolution. Right now the product line for specialty fiber splicing is represented by three main pieces of equipment. It is S183PM2, sorry, S184 PM SLDF, and S178 LDF. So a little bit about fusions, about splicing of specialty fibers. So due to the due to the innovations and the development of fiber lasers and all the field, the fiber lasers become very popular because they allow to process materials, and they are used actually in many industrial products like marking, microprocessing, and welding, soldering. So fiber lasers can be broken due to the lifetime, etc. And in order to repair the fiber lasers on site, we need some kind of splicer, the splicer for large diameter fibers. So it is to be compact and small sized. So what is large diameter fiber? Large diameter fiber is used to transmit high power laser light in the field of medical devices and laser processing machines. So the typical clad diameter of these fibers lies between 200 micrometers up to 1000 micrometers. You can actually meet some specialty fibers of even more than 2 millimeter diameter cladding. So recently the demand of large diameter fibers is increasing. So if you participate in different conferences and exhibitions that are devoted to material processing and for example metal cutting, you will see that the most part of lasers are actually the fiber lasers right now. And yeah, you just need fusion splicers to let it work, because everything can be broken. So fusion splicer to large diameter fiber should have the function to generate high power arc discharging in order to splice it really well. You can see it here. So these three main pieces of equipment with part numbers S184, 183 and 178 LDF. We see here the brief table the brief table with a description of what actually this splicing machine can make. The S180 series can both splice make the high strength splices, make the PM fiber splice, but they are not handheld operation, and they don't work with battery. Actually, we have the demo unit with us here. It is located in the hall, and I will gladly provide you the description and demonstrate you the splicing methods that I applied. So we need to know that actually this handy splicer can splice the fibers up to 480 microns, but when it comes to the diameters larger than that, we need to use 183 that splices up to 500 micrometers, or 184 that splices up to 1,200 microns. So what fibers are what fibers can be spliced with these splicers? One of the most important specialty fibers types is polarization maintaining fibers. The birefringent fiber, I think it is the best description of it. You can see here on this slide, you can see here the main types that I used. Actually, it is the well-known panda type, the bow tie fiber type, the elliptical core fiber, and the tiger fiber, or the fiber with elliptical stressing cladding. So these splicers can splice both the polarization maintaining fibers and the large diameter fibers. So one of the main features is that it can splice dissimilar fiber as well. So the optimized polarization maintaining fiber image recognition allows to splice various type of panda fiber. It can splice high index fiber, erbium dope fiber, photonic crystal fibers as well. It has the function of advanced arc discharge control, and it can be used for manual splicing of unknown fibers. We can see here on this image that actually the splicing machine, the splicing tool, is using the method of scattering pattern analysis. So we just enlight the fiber with the monochromatic wave, plane wave, and then on the camera just we can see here not the profile of the fiber, but the scattering pattern, the diffraction pattern. So if we use some kind of fiber with compensated with the stress rods with compensated refractive index, actually we just need to use some additional equipment to know exactly the position of the birefringent axis during the splicing process. So another main feature is fast splice time. It is really easy to operate with. The splice time lies between 15 seconds up to 35 seconds. So the heating time of the protection sleeve is also fast as well. It lies between 51 seconds up to 40 seconds. So I will be a little bit more brief about fiber splicers. So actually these splicing machines can automatically perform a tensile proofs test for the splice fiber, then release the holder lid to avoid twisting. It is really cool. It is really nice because if your fiber is a little bit rotated and there is some mechanical stresses inside, it can really damage your splice. It can make the splice with bigger losses and with worse extinction ratio. Splicing dissimilar fiber mode automatically adjusts the arc discharging based on the fiber profiles and achieves the low splice loss. It doesn't require changing and selection of the fusion program, even if you splice different types of fiber. Here it is. Here it is the description. So here we have two fibers of the same cladding diameter but with different core diameters. So we need some kind of taper to reduce the splice loss because the overlap integral of the propagating modes is really different if we use such type of splicing. So here we see that our splicing machine can perform the arc scanning and arc sequence function to allow to perform wide variety of arc discharge to minimize the splice loss. If you are into using the polarization maintaining specialty fibers, you know that all kind of research institutes, universities, fiber fabrication companies, even if they up to the panda fiber, they all use different stress rods diameters, they use different doping materials, different concentrations, and actually all panda fibers are a little bit different. For example, the Fujikura ones, the perm fiber, I guess somebody who works with Russian specialty fibers know the perm one. So here we need to know that there's a diffraction pattern is actually a little bit similar, and our machine allows to analyze automatically the profile, the scattering pattern, and to actually it makes a new program to splice the new panda type fiber as well. So we are able not to send this fiber to the fabricator of the splicing machine and so on. We just can do it on site in the laboratory. So one of the main features as well is the certain software. I think that the thing to highlight is that we can actually control the splicing machine not only by the interface on its on the splicing machine itself, but with our PC. So it can be really of high use if we work in the laboratory. We have some external equipment, for example, extinction meters, the Michelson interferometers, in order to splice really well, to have good splices, but we need to control all this equipment on site. We have a really huge laboratory table, and it is inconvenient just to go all around this table, but we can control all our devices just from our PC. So it has the function of manual splicing and semi-manual splicing, semi-automatical splicing. This is really important if you work with specialty fibers that are made of not that a really big volume. So you can do whatever you want with this splicer. Actually, you can. It is really convenient to. It is really comfortable to splice photonic crystal fibers of different kinds to make some kind of tapering, because you can't actually get really nice taper if we use the splicing machine. But anyway, for some applications, for some probes, it is suitable. So that was all about 183 and 184 splicers, but you probably heard of the same splicing machines that are all around. What is so special about the product line? The special thing about product line is the use of the ring of fire technology, the technology that was patented by 3SAE. The 3SAE is the United States company, and they are partners with Furukawa, with Fitel. So if you go on the 3SAE website, you can actually see the promotion, the advertisements of Fitel Furukawa splicers, and if you go to the Furukawa website, you can see the same promotion of the 3SAE products as well. So the main point is that in order to splice really the fibers of really huge diameters, we need a really big field of uniformly heated area. really huge, uniformly heated area, and you can't you can't make it with just 2 electrodes. So our American partners, they just use 3 electrodes. Actually, it is just ground and 2 faces. So this allows just using one splicing machine not only to splice small fibers, the fibers of small diameter, the specialty fibers like PCA fibers, the polarization maintaining fibers, but the fibers of really huge diameters as well. This is really useful for labs, for lab equipment. It is a really nice solution. So you see here, the operator just tried to splice the fiber of big diameter with conventional 2 electrode method. So we see that the plasma current actually goes from one of the sides, one of the lateral sides of the fiber, but it doesn't affect all the lateral side, all the splice. So here it is the summer specification. We just need to know that S183 just splices the fibers with diameters from 80 up to 500 microns, and 184 is used to splice from 800 up to 1200 microns. Okay, so we go up to North Lab and 3 SAE. Just ending with Ring of Fire and starting with Ring of Fire again. So North Lab is the fiber optic competence center in European Union. You have already probably heard of such company as Ericsson, and you probably heard that Ericsson were fabricating fusion splicers as well. In some labs you can actually see their old equipment. And North Lab is founded by 2 people who were just actually working in Ericsson and then founded their own company because they didn't have any job. But actually this that was really nice hint because they just started to work with 3 SAE and with us. And they actually found a really nice solution in fiber processing, in glass processing. So these pieces of equipment that I will be talking about, they're used for the most advanced fiber glass processing, and it is actually made, all this technology is actually made with the main universities such as MIT or with such companies like IPG. It is one of the best suitable technologies just to make fiber splicing and glass processing. So here you can see actually the graph of the distribution of the temperature in the special distribution of the temperature. You can see the really wide area that I was talking about of uniformly distributed heat. So we have actually 4 pieces of equipment that are the main stations that are actually used in the main laboratories and by the main fabricators of passive components and laser components, fiber lasers. So the most important one, in my opinion, the most important one for Russia is the LDS system. So you can see here that it is actually a really nice piece of equipment, and it almost looks like the laboratory setup. And no wonder why, because it is actually constructed, it is designed just to allow the engineers of 3 SAE, the engineers of North Lab, to adjust it in order to fulfill all the requirements of the customer. So it is multifunctional. It can actually it can perform splices from 50 microns up to 2.5 millimeters due to the use of this Ring of Fire technologies. It has the inside cleaver that actually allows to cleave, for example, the bundles and the combiners, just not getting it out of the system. It has the option to make tapers that are really of great use in fiber lasers. The mode field adapters, ball lenses. You probably heard of ball lensing because here in Samara there are a lot of people with problems of kidney stones problems. Thus, there is the innovative technology that is actually used in the United States and European Union right now. They use the fiber with ball lens, so they just get the fiber with this probe inside of the person's kidney. Then they couple the laser radiation of high power inside and treat the kidney stone without actual surgery. So that is the new method, and that's why ball lensing is that popular right now, due to the medical purposes. So this is one of the cheapest and the most suitable pieces of equipment, the LDS system. So all the equipment actually is used in research and development, manufacturing of optical components such as combiners, mode field adapters, couplers, lenses, end caps. You have already probably heard of end caps. End capping is used just for fiber lasers to reduce the optical power distribution, the special optical power distribution. So here are the best samples. Every producer, every fabricator, every company has the number of pictures that allow to demonstrate what the system actually does and what the system actually allows to make. And this one is the same. So here we can see the perfect splice of the 2 millimeter fiber up to the conventional 125 micron fiber. The splices of the hexagonal fiber up to the large diameter fiber. The photonic crystal fiber of huge diameter up to the same fiber of 2.5 millimeters. Here we can see the pump combiner, 4:1, 7:1 fiber combiner, and taper. So these are one of the main things that are actually made with these systems. I need to note that the North Lab and 3SAE actually they collaborate with universities. They understand that that not that much actually people and companies can allow to buy such expensive equipment. That's why they actually do some things for free in order to invest in the field development, because some of the engineers they just might work in 3SAE as well, and they might actually purchase the systems. Here are another samples. This one is actually a really interesting sample. We can see here the tapered fiber, the capillary that is actually fused to this fiber, to the lateral surface of this fiber, and then it is just tapered as well. And you can see such probes on YouTube, because these are the ones that are used to treat prostate right now without surgery. This is really innovative and really nice. This is the method of end cap in holding. So in order to hold in the system the end cap of really small size, we don't use conventional holders. We use the vacuum holder. You can see here the small tube. So here is the vacuum. So there is a small pump over here that sucks the air out, and that's how the end cap is held. Here we can see the
5 minutes.
5 minutes left. Okay. Left. Okay. So the TMS station is pretty much the same. It is used for tapers manufacturing. It uses thermally stabilized plasma. The CMS is actually the combination of LDS systems and the TMS. It is one of the most representative pieces of equipment. Here is the lens forming station that is actually the best suitable pieces of equipment for medical purposes, for fabricating fiber probes. The company actually has in their product line some stripping machines for polyamide covered fiber as well, for cleaving, polishing, tensile stress testing. We have with us the demo unit of ProCleave LD, the ProView. The ProView is the compact interferometer in order to analyze the facet of the fiber, the cleaved facet of the fiber. To analyze the interferometric pattern, you actually need to be a rocket scientist, but our piece of equipment is really small. It is really popular right now. It actually allows you just to make, the operator just sees the 3D picture of the cleaved area. So, here is some information about the FBG manufacturing solution. This is Noria. Actually, it uses the phase mask method. You need to use the diffractive resonators, the fiber break gratings in order to make the distributed sensing and to make the high power, in order to apply it in high power lasers for making a resonator. So in order not to use the really complex equipment in the lab, we just use the really nice and small piece of equipment that uses the phase mask method in order to fabricate a lot of FBGs at the same time. So here we see that we can actually inscribe different kind of fiber break gratings in one fiber using different types of phase masks. Here is the brief description. It uses the argon fluorine excimer laser. You can use really nice handling structure. So this is how it looks like. I think that it is the best solution for people who want to massively fabricate the FBGs. It has the ability to actually inscribe the oxidized gratings as well. So, few words about FiberPro. The FiberPro is Southern Korean company that actually into the automatic aligning, bonding, and test systems for optical devices. The three main systems, the IFA 600, IFA 640, and IFA 700. So all these pieces of equipment are actually into working with soy and wafers in order to splice fibers up to different kind of structures to align it. It is one of the most popular equipment right now in Asia and Europe for making MIOCs for fiber optic gyroscopes and modulators. So we are representative of Luna as well. So Luna makes a lot of equipment, but the main equipment is actually the high precision reflectometers. We have the demo unit with us, and I will talk about it for a long time if you are really interested in it. But the most important thing that you need to understand that this piece of equipment actually is used in order to control the optical lines with a really high resolution of 10 microns. So, to make it more brief, here it is. You see here just the simple connector, and the resolution is that high that you can actually identify the different losses that actually and reflections that appear along this connector, and it is really useful. So it is used in different fields of photonics and radio optics as well, radio photonics. So I think that I'm in time right now.
Yeah,
Is it okay? Yes. So the last part was really brief, right? So thank you for your attention. Yes.
раз, раз, два, три, раз, 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 два, три, раз, 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 два, три, раз, 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 два, три, раз, 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 раз. Ну, сейчас может звать так, вот так. Раз, раз, два, три, раз, 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 два, три, раз, раз. Раз, раз, два, три, раз, 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 два, три, раз, 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 раз.